time. So we are going to introduce our next speaker here. We have Marcel. Marcel's going to, talk to us about Taming Anycast in the wild internet. And Marcel completed his computer science and PhD at Northwestern in 2016. And his research has been on enabling, additional channels of communication in existing networks and improving network performance. And since then, he's worked as a research scientist at Verizon Digital Media, where he has further explored transport layer optimizations, large-scale management strategies, and cache optimizations. With that, Marcel, thanks for being here.
Yeah, thank you so much for the intro. So today I'll be telling a little bit about a system we built for managing Anycast on the internet. So we call this Taming Anycast in the wild internet, and with the undernote here, under duress, because we're going to talk a little bit about some of the challenges that we faced with the COVID-19 lockdowns. I do want to give credit where it's due here. A lot of this work was actually originally done by my intern from a few years back, Stephen McQuiston, who can be found at the University of Glasgow these days, and our colleague at the time from the traffic management team, Sri Priyanka Uppu. So this work actually originally appeared at IMC 2020, the Internet Measurement Conference, but this has some relevant COVID-19 updates. So we'll go to the next slide and dive in here. So just to give a little bit of context on the sort of environment that we'll be talking about today. So I'm from the Verizon media platform. You may know us by one of our older monikers, the Verizon Digital Media Services, or the EdgeCast CDN. So we have a big multi-tenant CDN, right? We're not just an internal Verizon service, but we do regular business-to-business CDN services, and we're global, right? We're spread all over the world. And one of the really interesting features that our network has is a large number of interconnects, right? We have these points of presence, and each point of presence is connected to many other networks. And that's actually going to be sort of the interesting thing, right? It's gonna create a lot of opportunity for us to do fast and efficient delivery, but is also going to create some challenges that we sort of have a proposed solution for. So if we hop over to the next slide. So our CDN today uses Anycast for delivery. So this is in contrast to a sort of DNS-based load balancer. There's a few different ways you could design such a system, but right, DNS is a very common one where when a user wants to request content from the CDN, they resolve a name which has a load balancer sitting behind it, and then that makes a decision about which server to send you to. And that works very well for a lot of setups. But what we use instead is something called BGP Anycast. So what we do here is from each of our points of presence, which I have a sort of little sample here labeled as these blue squares, we announce the same IP prefix. Right, and the idea is that once we've multi-homed, right, those announcements will propagate out into BGP, right? And when a user wants to connect to our network, right, they send a request to one of those addresses, and rather than making an explicit choice about where they should go, the network decides for us, right? Those routers in the middle will do IP routing as normal. They'll use their BGP tables, and they'll choose one of these sites. Now, this is really handy. It gives us a lot for free. For example, we don't have to make any sort of critical path decisions on where to send users, right? We don't have to have that load balancer hiding behind the DNS resolution. And because BGP prefers shortest paths, this mostly works out. So most of these green dots, which sort of represent clients, go to the sort of closest blue square, closest for some definition of network closeness. Now, this also buys us a few resiliency features. Right? If we need to take a site down, instead of having to drain connections slowly over a long time, what we can do is we can withdraw the BGP announcements, right? Which will cause the BGP tables to sort of smooth out, and traffic will get sent to other locations, right? This makes certain management tasks a lot easier. But we'll see that because we're depending on the network to make decisions, it sometimes doesn't do what we want. So if we hop to the next slide, you can see an example of that. So here is kind of this is a little bit reductive, but I think it illustrates the point well. On the left, we have a little blue square that symbolizes a point of presence in California. On the right, we have that yellow square, which is a point of presence in Colorado. And then the circles here are end users. And in this example, they come from two different ISPs, the purple ISP and the green ISP. And for whatever reason, when they send connections into the network, right, they're sending us HTTP requests, and they're getting routed through regular IP routing. They're getting sent to that California location. Now, functionally, that's okay, right? They're getting their content, everything's sort of flowing properly, but they're going kind of far away, which means they're potentially paying some latency penalty, right? It may take, say, 35 to 45 milliseconds to get that content from California, which is starting to get into the range where it's user detectable and might start to degrade their experience a little bit. But even worse, there's a better choice, right? We can see that there's that point of presence right there in Colorado that they could be connecting to instead. So what I want to do is I want to break down this scenario a little bit, and we'll look at one of the potential causes of this and what we can do about it. So if we hop to the next slide. So here's kind of a simplified explanation of what might have happened there. And there's kind of a lot of arrows here, so we'll walk through it carefully. So on the left, we have site 1, which we can sort of pretend is our California site in the previous slide. And on the right, we have site 2, which we can sort of pretend is that Colorado site in the previous slide, right? And so those are our 2 points of presence, and they're announcing the same Anycast address, right? And then we have this gray circle in the middle, which represents the end user, and he lives inside some ISP, which we're going to label ASB. Now, it could be that ASB and ASA both buy connectivity from some provider, Transit Z, right? And this is going to be a customer-provider relationship, right? Both ASA and ASB are going to pay Transit Z for this connectivity. And that's a very usual way to get connectivity on the internet, right? That's kind of the model. It's hierarchical and has this kind of relationship. But it might also be that ASB has another connection through another network, which we're going to label Peer X. And it might be that this Peer X is not one of these customer-provider relationships, but instead is a peer relationship. And it might be that ASB has a sort of settlement-free peering arrangement with this peer, which is to say they've agreed to carry each other's traffic without cost. And it might be that actually ASA has the same relationship with that Peer X, but in California. So what's going to happen is ASB is going to have this packet from his user, right, that SYN packet to start the connection. And he's going to look at his routing tables, and he's going to have to make a decision. And he's going to say, should I send this to Transit Z or should I send it to Peer X, right? Both of these are valid routes for reaching ASA. And probably what he's going to do is he's going to say, well, these routes are the same length, so I have to break a tie. And if I have to break a tie, I'm going to go with the cheaper one, right? I'll send it to Peer X where I don't have to pay for it, and everybody will be happy. And he's sort of not wrong to make that decision, right? That's a fine configuration for a network. So he'll send that packet to Peer X, who will send it along to site 1, who will get the request and service it, but at some latency penalty. So what ended up happening here is the request went to site 1 instead of the much closer site 2 due to some policy that ASB had cooked into their network. And again, it's not that ASB made a mistake, but I think the scary thing from the perspective of the CDN is that that's policy we can't necessarily see, right? We don't necessarily know what choices ASB is going to make, right? And it's sometimes not until it happens that we know these are going on at all. Now, there's a couple of different remediations you could consider here, right? There's sort of a lot of classic sort of network engineering tricks you could do. For example, the most straightforward perhaps is that ASA could try and add peering with Peer X at site 2, right? Make this a sort of non-issue. There are lots of reasons why that might not be tenable. Maybe they're not in the right data center or things like that. Maybe Peer X's router is full at site 2, so it's just physically not an option. Another old-fashioned technique could be to call up ASB on the phone and say, hey, you guys are making a routing decision that's hurting your customers. Maybe we can work something out, right? And maybe we can get them to adjust that policy. But not all of these are sort of scalable, right? It works if this happens once, but what if it happens a lot? So next slide, please. So what I want to do is I want to take a little step back, and I want to think about what makes this kind of scenario so tricky to deal with in real life. Next slide, please. And the issue really comes down to 2 categories of networks, right? And these are a very qualitative feature, or that maybe there's not a super tight description for, but I think they sort of convey the nature of the problem well. Which is, the first is there's a type of network that I'm going to call few provider networks, and this is actually what most networks in the internet are, right? They have maybe one transit provider and a handful of peers. And if they're lucky enough to maybe be connected to an IXP, they maybe pick up tens of peers at that IXP, or hundreds in some cases, right? So, but generally speaking, they have a small number of next hops available to them. On the other hand, on the next slide, we can see another type of network, which I call many provider networks. And these are networks where you have many transit providers and many more peers, right? And if you run an Anycast network, you might have many sites where you have many transit providers and many peers at each of those sites. And when you're in this kind of situation, right, you don't necessarily have the ability to sort of suss out every interaction that'll occur between these peers, right? As soon as you're talking about hundreds of peers, or as we saw in that initial slide, 5,000 interconnects, it suddenly becomes extremely difficult to figure out who has what relationships with who and what sorts of policies they might have, right? You can make some guesses about who's a provider and who's a peer, but it becomes very tricky very quickly. And next slide, please. So this is just to give a sense that this is a real thing, not just a construct I invented. So one of the things we looked at is we tried to understand how different Anycast networks compared in terms of the number of providers. So what we considered here is the number of clearly available next hops in public routing information. So this comes from the route tables we can collect from the Route Views project. And here what we looked at is we looked at the DNS root letters, the A through M root letters, which are running Anycast networks. We looked at our own CDN, which is labeled CDN, and we looked at a popular open recursive resolver that we labeled GDNS that also runs on Anycast. And what we saw is from this publicly visible data, which I do want to say is certainly not all connections, but is some subset of them, we see two clear categories emerge, right? There's the category which is largely on the left, where we see the number of peers is very low, right? In some cases, it's sort of only one. In some, it's a handful. And then we see a category where there are many provider networks, right? Hundreds in some cases. And this suggests us that this is indeed a real distinction, right? That there are sort of two different administrative configurations that are going to have these very real performance impacts. Next slide, please. So what is an Anycast network to do, right? How are you going to figure out how to configure your network so you can avoid these kinds of issues, right? Where traffic is choosing some peer due to some policy and choosing a suboptimal Anycast site. What you can do is you can kind of think about the situation as a matrix, right? Along the x-axis, we have our Anycast sites, and along the y-axis, we have all of our providers. And then you can say for each site and for each provider available at that site, should we announce our Anycast blocks out to that provider, right? And you can kind of think of this as a big binary matrix, right? You can switch each one on and off, and they may have different performance outcomes when you do that. So next slide, please. So that's sort of the overall thing. But an important thing to keep in mind here, and I think something that makes this challenge a little bit different than some of the other sort of popular traffic engineering questions that have been raised recently, is that Anycast is ultimately a question of inbound, right? We get a request from a client, which is going to be routed to an Anycast address, which is going to be small data, right? This is going to be an HTTP request on the order of bytes. And we're going to send a response back to that client's unicast address, right? And that's going to be a big response on the order of megabytes, perhaps, right? If you imagine streaming video, they're sending many of these small requests and they're getting very large responses. And so what this does is it means that once a request arrives, we need to answer it, and we need to make sure that we have the capacity to answer it at a particular location. So that means when we're changing around these Anycast configurations, we're changing how traffic is coming into our network, which in turn changes how we can push it out of our network. And that really makes things complicated. The analogy I really like for this is it's kind of like driving a car while looking in the rear view mirror. You have to kind of remember, like, you turn the steering wheel this way and the car is going to go the opposite way, right? So it makes it a little more complex than just traditional egress traffic steering. Next slide, please. So the first thing I want to look at, though, is how much does it actually matter, right? This sort of California example was maybe a little bit contrived, right? Maybe I picked that because it had a nice picture on the slides. So what we wanted to do is on the next slide, we wanted to take a look at how we could actually measure this, right? And understand what impacts we had from these kinds of configurations. So what we did is at each of our Anycast sites, we defined two groups of providers. The first is what we're going to call the control group, right? And this is going to consist of just our transit providers. This is kind of the most conservative set you could choose, right? These are the providers you need for full connectivity to the internet, right? So that's our control group. And then we're going to define a second group, which we're going to call the experiment or the experimental group, which is going to be both those transit providers and all of our peers at that location. And what we're going to do is we're going to take two Anycast addresses, and these are special test blocks that we can manipulate without impacting customer traffic. And we're going to announce one of them from to just the control group, and the other to just the experimental group, or well, to everybody basically. Next slide. And once we have these configurations set up, we're going to do some measurements. And to this end, we're going to use the RIPE Atlas distributed measurement platform. For those unfamiliar, this is a program set up by the RIPE NCC out of Amsterdam, and it consists of about 10,000 globally distributed devices. They're these little hockey puck size measurement probes that you can put in your house. I have one in my living room. And once you participate in the program, you can run experiments from these different probes. For example, you can do pings and trace routes and some limited HTTP gets. So that's what we're going to use for our measurements here. Excuse me. It's worth noting that the measurements here aren't exclusive to RIPE. You could actually use any platform in which you can do trace routes. The key is we have to simulate that user experience. We have to be able to measure from outside the network in to us. And for some convoluted technical reasons, we need to be able to do trace routes. So on the next slide, I sort of show what we do then is we measure these control and experimental groups using these probes. And then we group the probes together, right? Each individual probe might be a little bit noisy, right? Somebody might be downloading game updates, for example, on their home internet, which will maybe cause a little bit of cross traffic. So what we do is we group the probes by AS and geolocation, which is to say by ISP and their physical location, either country or state in the United States. Next slide, please. So what we see is once we measure from all these probes and we measure these two configurations and we look at the difference in round trip time performance, right? And on the x-axis here, we have the relative change between that same probe's performance with the control group versus the experiment group. And on the y-axis, we have the CDF of groups. So what we can see is that for about 60% of those groups, they saw improvement, right? Things got better. And that's consistent with our expectations for how peering works. You add more peers, you get better connectivity, right? You maybe have more shorter paths, so things are better. So we were glad to see that 60% improvement. On the other hand, about 40% of probe groups did not get better. In fact, some of them got quite a bit worse, which suggests that actually this concern about these types of policy scenarios like we saw before are valid, right? And we do need to be careful. We can't just announce to everybody and hope for the best, right? This is going to require some careful work. Next slide, please. So this is just an example to show you how things can sometimes get a little bit out of control. So this is an incident we had a couple years back when we tried to turn up a new provider in a location, and there was a small misconfiguration in how that happened. And as soon as we started announcing that to that provider, we started pulling in clients from all over the world, which was not the intended effect. So the red dots here show you during the incident and the black dots immediately before. Now, luckily, this triggered a couple of sort of circuit breakers that we have. So nothing bad happened here, but it was definitely scary and sort of goes to illustrate the danger of misconfigured Anycast in these cases. Next slide, please. So the last thing I want to talk about from the sort of defining the problem space is keeping in mind that there are pretty wildly different network volumes, right? Different ISPs have different numbers of users, and those users request different content from the CDN. And what that does is that can cause really uneven load. And that gets even worse when Anycast behaves unpredictably. For example, in this little example I have here, ASB may, for reasons like we saw earlier, begin connecting to a faraway site. And that has the sort of round trip time performance implications, but it also means all those users under ASB are now connecting to site 2. And that's potentially putting a lot more fresh load on site 2, which may create its own problems, right? So this isn't just a question of round trip time performance, but actually of true traffic management, right? Of controlling traffic volumes. Next slide, please. So what I want to look at now is I want to take a little look at what's happening today, right? In particular, in light of the COVID-19 lockdowns and the impact that's had on the internet as a whole. So on the next slide, what I have is the number of requests taken from a single POP. Now, I've had to do a little bit of anonymization, so sorry about that. But what we have is the red line showing the request rate for a week in March, and the black line showing the request rate for a week in June. And we can see that this week over week difference is profound, right? We see about a 25% increase in total request count over this period, which is significant, right? I mean, as other speakers have talked about today, right, we have sort of planned organic growth, and then we have sudden growth. And this was firmly in the sudden category. On the next slide, we have the same point of presence for the same set of weeks, but here, instead of looking at the requests, we're looking at bandwidth. And here we see that the bandwidth out actually increased even more dramatically, right? Almost a 50% increase, right? And that's interesting because that means not only did we see similar, large increases, but we see that users are asking for larger files. This sort of is what we expect maybe as certain things like streaming, video streaming became even more popular, right? People are at home entertaining kids, things like that, which creates a certain traffic pattern. Another interesting thing, which you can see a little bit on this graph, is that the diurnal peaks widened a little bit, right? So we got busier earlier in the day, and that persisted a little bit later in the night. Next slide, please. Another interesting thing that changed dramatically is where traffic was coming from, right? So here what we're looking at are what we call eyeball networks, right? Networks that have end users in them. So this is a handful of eyeballs at a single point of presence, right? Each line is a different ISP. And the y-axis here is sort of normalized to the pre-lockdown maximum. And what we can see is that over the month of March, the amount of requests coming from these eyeball networks increased dramatically, right? About 20% for some of these. And because many of these are sort of our largest source of traffic anyway, that's a pretty dramatic change. On the next slide, you can see that when we consider, we bump to the next slide, please. When we consider wireless providers, we actually see the opposite trend, right? And this makes sense, right? User mobility has decreased, right? People are hanging out at home. They're using their home internet instead of their wireless provider. So it's not a surprise that this dropped. But what this means is that our sort of traffic matrices have gotten a little bit scrambled, right? Places that were big sources of traffic before have decreased slightly, and other sources that were big sources before have increased slightly, or not slightly, dramatically. So on the next slide, what we can see is that these big changes are sort of swinging things around. We're moving a lot of weight on the internet. And because these were some of our biggest contributors, that means we're truly talking large volumes. And when we're doing all that, we need to know where traffic will go, right? If we're going to make changes in the network, we're going to add new peers, we're going to change our BGP announcements, we need to know what is going to happen, right? Otherwise, we risk breaking things, right? It's kind of like redlining your car, right? If you're pushing it really hard, you want to make sure that you know what's going to happen next. Next slide, please. So what do we do? What we're going to propose is a system called DailyCatch. So what DailyCatch does is it allows us to take snapshots of the behavior of different configurations. So for example, we can consider those control and experiment configurations that we saw before, right? We can measure how each one worked, and DailyCatch will allow us to compare them and tell us, A, what happened for different groups, so we can see who improved and who got worse, but we can also distill that into a combined score, which will allow us to make better decisions sort of on a large scale. So on the next slide, you can see sort of the workflow that DailyCatch has, right? We use, again, the RIPE Atlas platform, but again, any measurement platform with sufficient visibility will do. We send trace routes to our control and experiment groups. A lot of times our control group is our current production network, right? We want to compare how things are today, and our experiment group is a set of test blocks configured on sort of a proposed change. For example, a new provider or a shift in our policy. We do those measurements, and then we convert the round trip times that we measure into this weighted score. And we do this so that we can sort of easily compare them without having to look at relative differences all the time. We then weight these scores by the volume that we see coming from each of those networks, right? There are certain networks that are just a little bit more important, right? Eyeball networks with end users to them are critically important. Strange enterprise networks that don't actually provide that many requests to the CDN just don't matter as much. So we sort of weight them accordingly. And then we combine these scores with a simple sum. And this allows us to say, okay, did that experimental configuration result in better performance for more users? That is, did the sum go up or down? And the other thing we can do is we can look at individual groups and say, okay, with the experimental configuration, who got worse? And then we can try and understand why they got worse. Next slide, please. So if we want to return to this original example, we can imagine that, say, this scenario where these Colorado users are connecting to California is kind of our control configuration. Maybe that's what happens in production today. And we could consider some experimental configuration where perhaps we added peering with that peer X at our site in Denver, wherever that is exactly. And on the next slide, we might see what might happen with that experimental configuration. Right here, all those users are now connecting to the closer Anycast site, and as a result, are seeing improved performance, which would then result in an improved score. Next slide, please. So here's actually a pretty cool measurement we did using those original experiment and control configurations, where we saw that not only did some configurations make things better for different networks, but that actually the impacts are not uniform within the same network. So this is from a single residential ISP that we measured. And with one of the configurations, we saw some behavior, and then we considered the experimental configuration. And if you look at the dots here correspond to the right axis, the improvement or negative improvement in milliseconds. We can see that on the far right, the customers in Massachusetts and Colorado saw significant improvements in performance, but customers in New Mexico actually saw significantly degrading performance, right? And this was due to a convoluted set of routing choices. So we were able to see this, though, because the groupings clearly highlighted these differences. And that allowed us to dig in and address these directly while still pursuing the gains that we were able to achieve on the right there. Next slide, please. Another cool thing we can do with DailyCatch is we can consider snapshots over time. So instead of considering explicit configuration changes, we can look at how things change on a fixed configuration over time, right? And we can, for example, collect these snapshots every day and look at how performance has changed over the course of a month. And this is important because, as we saw, a lot of these ultimate behaviors are determined by choices that happen inside the network, outside of our control, which means that they may change arbitrarily. So by measuring over time, we can see when those happen, we can see when things degrade, and we can see specifically how they degraded on the group level, and we can address them more effectively and more quickly. Next slide, please. So overall, these many provider scenarios offered just a great deal of flexibility, right? We have more peers, we have more shorter paths, we have greater resiliency, right? Things are good. But it comes with significant challenges, right? If you want to run an Anycast network in this scenario, you're going to have to do a little bit of relationship inference, and you're going to have to manage volume, right? You're going to have to know which users are going to go where. And DailyCatch provides crucial understanding of these interactions without having to measure each one individually. So we've had it deployed for a couple of years now at this point, and we found it to be a very handy tool for addressing these types of challenges. So that's all I have today. Thanks very much to Thousand Eyes and the folks for putting us on and having me.
I think your mic might not be on actually. Sorry.
No, thanks. Thanks, Marcel. I was just going to say this is a really interesting talk. You were talking about how in running a large Anycast network where it's sometimes hard to predict what the impact will be of some of the changes that you make. Looking at it continuously and kind of getting that real world like visibility into what actually happens and what the impact is for users is just something that you just have to do on a continuous basis.
Yeah, exactly.
Yeah. And with DailyCatch, I assume this is sort of something you're again kind of like looking at every single day and then kind of incorporating like, the.
Yeah, definitely. It's one of those where you pop the dashboard open in the morning and you look at it and you go, what happened there, right? And